our diffusion is going to be driven from the alveolus to the blood. Okay? So as oxygen moves in, it's going to end up being dissolved in the blood first. Right? And so what are we adding to here? What value are we increasing? And remember, this is going to be refreshed. Each time you take a breath, the oxygen that's moving out of here is going to be replaced by another breath. Okay? So this is going to be constantly replaced. So as we move oxygen in here, and this is occurring as it's flowing through the lungs by different alveoli, what value, what measured value are we increasing as we move oxygen into the plasma? Partial pressure. Okay? So we're increasing the arterial, because this is venous, it's the pulmonary veins and it's capillaries, but it's going to become our arterial blood. This blood is going to go back to the heart and be pumped out of the heart by the ventricles and go into the aorta. All right? So this is going to be our arterial oxygen value. So this is arterial CO2. And that's the value that you see at the bottom of the graph, that A. PA stands for arterial partial pressure of oxygen. So this is going to be increasing until as this leaves the lungs and enters into the aorta after it passes through the heart, it's going to have equilibrated with the CO2 of the alveoli. All right? But we haven't yet finished the story about this. So as it moves in and this PO2 climbs higher, it's going to move from the plasma into the red blood cells. And it's going to bind to the oxygen. So every time an oxygen moves out of here to bind to our hemoglobin, what does that do to the room for more oxygen in the plasma? It's going to make more room. So as this is moving in, it's being replaced by the fresh oxygen that we're breathing into our alveoli. So this blood flows through the lungs, is picking up oxygen from the alveoli. As that fills up the dissolved oxygen in the plasma, that causes it to move, again, a gas pressure gradient, move into the red blood cell, where it saturates the hemoglobin. Once it's bound to the hemoglobin, it no longer acts as a gas. It's not bouncing around. It's not creating a gas pressure. So these are two separate values. So we're also increasing percent hemoglobin saturation. Okay? So the more oxygen there is dissolved in the plasma, the higher the percent of hemoglobin saturation is going to occur. So by the time the blood moves out, with everything being ideal, we have 104 millimeters of mercury equilibrated to our alveolar PO2, and we have 100% saturation, meaning all of the iron and all of our hemoglobin has bound an oxygen gas molecule. Okay? All right, so how does that relate to what we see here? Because everything I've just talked about is occurring at one particular area on this graph. To the left or to the right of the graph? Where is our PO2 the highest? To the left or to the right? To the right. So this is, again, not a percentile. This could go up to 110, 120 if we're breathing 10% oxygen, 30% oxygen, or 40% oxygen, or 20%. We could make this number higher. So this is not 100%. We can't get any higher than 100% saturation. Okay? So this side is percent hemoglobin saturation, the y-axis. The x-axis, the horizontal axis, is our arterial PO2 of oxygen in millimeters of mercury. This can go higher than 100. And I'm saying that because we tend to think that this is maxed out at 100 because we think of it as 100%. Okay, and it's not. It's actually 104, 106 right now. So, notice the line. So what we're saying is as we increase the PO2 of oxygen dissolved in arterial blood, we increase, right on the screen, we increase the percent saturation of hemoglobin. All right? So as we move in this direction, our percent saturation of hemoglobin is increased. Can you read that off of the graph? Okay? All right. So And there are two regions that are important. Notice how the line flattens out? So that if we get to 110 millimeters of oxygen for our PaO2, we can't saturate more than 100%. Okay, so that's why that line is flat. So it starts to get flat at about 90. Okay? Draw this a slightly bit more. So this region is talking about rephrase it, pulmonary oxygenation. Use the term that we started this lecture out with. For oxygen, this is our region of external respiration. This is where we're doing the gas exchange between the alveoli and the pulmonary capillaries. Okay? Now, do we want it to stay at that? If our hemoglobin would behave that way, would we want it to, would our tissues be better off if there was a higher oxygen affinity? So that we could get 100% saturation even when we had a PO2 of only 20. Would that be better? Would that be more ideal? We had a higher affinity between hemoglobin, between the iron and the oxygen. We could go up to 10,000 feet and still have as much oxygen saturation as we do at sea level. That would be better for us, right? Except, it really isn't. Notice this area? This is internal respiration. A high affinity for oxygen would mean that we could easily saturate our hemoglobin at 10,000 feet. Unfortunately, it would also mean that as the oxygen in our tissues fell, because we're using it for cellular respiration to make ATP, the oxygen would not dissociate, it would not come off the hemoglobin. And it would just stay bound to hemoglobin, and the hemoglobin would get back in our lungs and still have all the oxygen, and our tissues would be starving for oxygen. So we actually need both of these situations to occur. We need the hemoglobin to get saturated when we have a high amount of oxygen available, and when we don't, we need the oxygen to come off of the hemoglobin more easily. Okay? So this whole graph is called the oxygen dissociation curve. And it's showing that as we increase the amount of oxygen dissolved in our blood, we increase the saturation. But you can read it in reverse. It's just as important. As we decrease the amount of oxygen dissolved in our blood, which is what happens in the tissues, as oxygen moves out of the plasma into the tissues, our PO2 is dropping. Remember what I showed you in that diagram? Draw a little bit of an alveolus here. So as oxygen moves out of the lungs into the tissue, into the blood, as more and more oxygen moves into the blood, more and more oxygen moves out of the blood and bound to our hemoglobin. So let's say now that we are in the tissues, we're not in the lungs. So here we have another cell. And it's using oxygen in its mitochondria to make ATP. So as this oxygen is leaving the plasma and going into the cell to the mitochondria to make ATP, what's happening to our PO2? It's dropping, all right? So we're moving this way on the oxygen dissociation graph. If hemoglobin had a high continuous high affinity for oxygen, this oxygen would not come off the hemoglobin. So, but the way it works with the tissue area, as this comes off and our PO2 drops now, this oxygen is going to come off and replace it and be able to move into the tissues. Because we're not there with oxygen and hemoglobin just to ride the circus ring around the body, okay? The purpose of this is to deliver the oxygen to the tissues. So we want to be able to saturate it when we have a lot available, but when we don't, we want it to be able to dissociate and come off. So this is identified as the plateau. And it's occurring in the lungs, okay? And our steep gradient is occurring in the tissues. Hence, external respiration versus internal respiration. So that's our standard component, and one way of looking at this is, now this is drawn at 40 and at 55. Usually it's drawn at 50. So it's, what would be our hemoglobin saturation if we have 50% saturated? What is our PO2? All right. So I'm going to redraw this and just start looking at where is our PO2 when our hemoglobin saturation is at 50%. So we know that we don't want to have a high affinity constantly. Would it be better to have a low affinity? And our line would be down here? No, because even if we were taking 100% pure oxygen, we'd only have 10 or 15% of our hemoglobin saturated. So this gives us the best of both worlds, the way our hemoglobin behaves, all right? So if we take 50% saturation, and we bring that down, it comes at about 30%, 30 rather, not 30%, a PO2 of 30. To 40. Now, what does it mean? So you can work this out, all right? Some students think that this is a difficult concept, what we're coming up to right now. But you can work it out. If it takes, instead of 30 or 40, if it takes a PO2 of 60 to saturate 50% of my hemoglobin, what does that tell me about the relationship between hemoglobin and oxygen? Is the oxygen staying on there better or worse? It's staying on there worse, okay? So what we're saying is, and we have to move this all the way over here to get 60%, and when I redraw my line, I see a oxygen dissociation curve that looks like this. It's described as the oxygen dissociation curve moving to the right. It means that the conditions have changed such that oxygen comes off of the hemoglobin more easily. A couple ways to think about this, all right? So let's say you're making popcorn. And if you increase the heat under the popcorn, it's going to pop faster. So you have to hold the lid on it to keep the popcorn inside the pot instead of popping out of the pot. All right, so think of the lid that you're holding on as the pressure of the increased oxygen that you have to have in the blood. You have to have that much more oxygen to keep the hemoglobin bound, the oxygen and hemoglobin bound together. Because it wants to leave. It's not attaching to the hemoglobin very well. So the factors that do that are factors that usually mean that we need more of the oxygen, all right? So, increase of amount of carbon dioxide. A lot of these overlap. Increase in carbon dioxide works by two different ways. Carbon dioxide will bind to hemoglobin. Carbon dioxide binds to the protein part of the hemoglobin, not the iron. And it makes it so it's not competing for the same binding site, but it changes the room that oxygen has to fit into the space with iron. So when carbon dioxide is bound to the protein part of hemoglobin, the oxygen just kind of gets popped out of place. Won't stay there, which is helpful because usually the reason we are producing more CO2 is because we're using up our oxygen, okay? So any factor that causes us up to produce CO2 is going to make it more difficult. So this usually causes a condition known as carbaminohemoglobin. In other words, carbon dioxide is bound to the hemoglobin. All right? Increased hydrogen ions. What does that say about our pH? Is it more acidic or more alkaline? We have more hydrogen ions. Anybody know from chemistry? Acidic. So increased acidity. Now we haven't talked about carbon dioxide yet. We will a little bit tonight and more on Thursday. When carbon dioxide binds with water, does anybody know what it makes? Carbonic acid. You're going to have this formula memorized because we're going to talk about it both now with the urinary system. So carbon dioxide plus water equals carbonic acid. And this will further dissociate and release a hydrogen ion and a carbonic acid. So not only does high carbon dioxide physically interfere with the ability of oxygen to fit, it also adds hydrogen ions to the blood. And the hydrogen ions themselves interacting with the protein change the shape of the protein, and that makes it difficult for the oxygen to bind. Okay? So, used to have folding chairs here. I used to play a one-person game of musical chairs. I'll just draw the diagram for you, all right? So think of the hemoglobin as a chair. And oxygen sits on it. And when the music stops, oxygen gets off, okay? So if we have a chair, it would work better with a folding chair. Actually, when music starts, you're supposed to get on, right? Everybody gets on the seat. Now, I'm sitting on the seat, I'm the only one here, all right? Now, I get up, the music starts playing. Let's say I'm over here when the music stops. I have to run around to get on the seat. What if there's 5 people playing? When the music stops, there's always going to be somebody available to sit on that seat. So the number of people playing the game is equal to the number of oxygen molecules, or a reference to the number of oxygen molecules we have available. So the more people there are playing the game, the more likely someone's going to sit in the seat as soon as the music stops. Okay? So that's our normal. Now, let's say that we change the seat, and now the seat, instead of being like this, looks like that. So as soon as I sit down, I immediately slide off, okay? Since I'm not sitting there as long, if I want to keep as many people, if I want to have someone constantly available to sit in that seat, what do I have to do to the number of people? I have to increase the number of people. Does that make sense? Because as soon as I sit and I slide off, that means I'm not occupying that seat very long. So as soon as oxygen binds to this seat here, it's going to slide off. So to always have oxygen on there, or at least 50% of the time to have oxygen on there, we're going to need to have more oxygen available than when we had the seat looking like this. Does that make sense? A bit? That's what we're saying. When we move our oxygen dissociation curve to the right, it means that to keep the same amount of oxygen, the same number of people sitting in their seat, when the music stops, we have to have more oxygen in the solution. We have to have more gas available. In reverse, what we're saying is it's less likely. Oxygen dissociates from iron more readily when the curve is moved to the right. okay? Or anything that causes a curve to move to the right causes it to be more difficult for oxygen to bind to iron. So, not only do we have, and I'll draw this picture over here. So this would be a regular C, okay? Increased temperature. What happens to your muscle tissue as you exercise? Temperature goes up, okay? So that higher temperature is going to make the oxygen have more energy, and it's going to dissociate from the iron more readily. So that's another factor that moves the curve to the right. Okay? Well, all of these happen when we exercise. So these are just examples. Exercise sometimes listed by itself, but it's going to increase temperature. It's going to increase the amount of carbon dioxide that's being released. So all of those are factors that are going to decrease the ability of oxygen to remain bound to hemoglobin.
Is the chair like specifically stands for the iron?
Uh-huh.
Okay.
Yeah. Okay.
And then,
So anything that causes the oxygen to slide off the iron means we have to have more oxygen available for it to maintain the same concentration. Not that we want to, that's just a way of showing the affinity.
and that just means disassociating?
Yes, it dissociates more easily.
Okay.
Okay, so here's what we mean by moving the curve to the right, a higher temperature, increase in exercise, an increase in hydrogen ions, an increase in carbon dioxide are all factors that are going to make oxygen come off more quickly. So to keep the same 50% saturation on our graph, the curve moves to the right. Okay. Now, all of those make sense. And here's a molecule that you probably haven't heard of before. 2,3, this phosphoglycerate or biphosphonate, the same CPG. This is something that red blood cells make, this molecule. And it does the same thing as carbon dioxide. It makes it more difficult for oxygen and iron to stay bound to the iron ion. And this is what red blood cells produce when they're in areas of low oxygen levels. Okay? They increase their 2,3-bisphosphate glycerate. It's made in red blood cells, and it's made in the placenta. So it releases, it functions to release oxygen. Guess what doesn't have DPG? Fetal red blood cells. Why? What does that mean about the affinity of fetal hemoglobin for oxygen? Is it going to be higher or lower than adult or postnatal? Higher. What? Remember the color we drew for the umbilical arteries? It was purple, but we called it deoxygenated. So the placenta is really getting, and then the umbilical vein, so it's really getting, when it's getting blood from the mother, it's getting the mother's level of oxygen. But it doesn't need to have as high a content because it holds on to it longer. So the whole component, the whole shift has changed. So since fetal hemoglobin doesn't produce BPG as much or use it as much, the fetal hemoglobin is going to demonstrate an oxygen dissociation curve that has moved to the left. Meaning you don't have to have as much oxygen dissolved in the plasma to saturate the hemoglobin the same amount. So we can saturate the fetal hemoglobin with less oxygen than in the adult, which we have less oxygen available to the fetus. It's breathing secondarily. All right? So here's my picture for moving the curve to the left. A partially collapsed folding chair. So you're bottom and way down deep in that V, and when the music starts up again, you're struggling to get out of that chair because it's collapsed on you. And the edge of the chair is up under your knees, and you've got to push it down and struggle to get out of it. So it takes longer for oxygen to separate from iron when the conditions have switched and moved the dissociation curve to the left. So not only do we have fetal hemoglobin over here, let me draw it on this side. But we see the reverse of everything over there. So even in the adult, if there's a drop in carbon dioxide, if there's a drop in the number of hydrogen ions, if the temperature is cooler, all of these are factors that would switch and move the dissociation curve to the left, meaning that the oxygen is going to stay bound to the iron ion longer. Okay? There's one more molecule we could put up there, which is not a good thing. Anybody know what it is? I talked about it a few minutes ago. Carbon monoxide. So carbon plus one oxygen is what we call carbon monoxide. Anybody know how this works? Why is it such a difficult component? So, carbon dioxide binds to the protein, the globin part, and makes it hard for oxygen to fit in place. Carbon monoxide actually binds to the same iron ion. So it competes with oxygen for the same binding site. That's one thing. The other problem is carbon monoxide is stuck where it is. It comes off much more difficult. It stays on far longer under these other conditions. All right, so when carbon monoxide is stuck on its iron, the other oxygens around it will not dissociate as easily. So the presence of carbon monoxide not only competes, so the hemoglobin is carrying less oxygen, but the oxygen it is carrying doesn't dissociate. So it makes it circuit through the tissues, and we get to the steep gradient, the slope here, and the oxygen doesn't come off, even though the tissues are desperately in need for it. So when the blood gets back to the lungs, we still have a lot of oxygen available. Our venous blood is still a bright red instead of the dark red that it should be, where it's given off oxygen to the tissues. That's not a good thing. That just means the tissues didn't get the oxygen that they needed. So with carbon monoxide poisoning, you often have cherry red lips and bright pink fingernails. It looks like there's lots of oxygen out there, but the tissue cells aren't getting them. Okay? So, treatment for carbon monoxide poisoning. You want to increase their PO2 by giving them increased oxygen to breathe, so that if perchance that oxygen, carbon monoxide did get out of the seat, there would be thousands of oxygen molecules ready to take its place, instead of just 10 or 20. So they could never have a chance to bind to that again, all right? Another way of doing that is to give the person oxygen under pressure. So put them in a hyperbarometric chamber, because that's going to also increase the amount of oxygen that dissolves in the blood if we give it to them under pressure. Remember that Henry's law? Let's give it to them under pressure, more oxygen is going to dissolve in the blood than if they just breathe it at a higher concentration. Okay. So on your lecture exam for this material, you sure you know what the x-axis is? That's the horizontal one, okay? And the value that we put on the x-axis isn't time, it normally is time when we do an experiment. It's our arterial PO2, okay? The y-axis is the vertical one, and that's our percent hemoglobin saturation. And then if I say, draw an oxygen dissociation curve for fetal hemoglobin or for high levels of CO2, know whether you're going to draw it to the right or whether you're going to draw it to the left, okay? And we don't draw a straight line. It's always in this sigmoid curve. All right, so before we look at carbon dioxide, let's spend a little bit of time talking about hypoxia. means low oxygen. Okay, hypo is low and oxia has to do with oxygen. So there's different causes of hypoxia. So hypemic refers to blood. So hypemic hypoxia, you have plenty of oxygen in the air. No problem breathing oxygen, right? You're not at high altitude, there's plenty of oxygen available to your lungs. There's plenty of oxygen in your alveoli. There's not a problem with your respiratory membrane, but you have a problem with hemoglobin. Okay, so if you are anemic, if you have pernicious anemia or you have hemorrhagic anemia and you only have half the hemoglobin you're supposed to have, you're going to have hypemic hypoxia, meaning it's not a respiratory issue, it's a blood issue. Okay. Now, stagnant hypoxia is also a blood issue. But that's a problem with volume and circulation. So if you have a weak heart and it's not moving blood through the body fast enough, you're going to have stagnant hypoxia. Okay? So it's just going too slow for your needs. You have enough hemoglobin, you have enough oxygen, but it's just not moving through the body as fast as the pump isn't working as fast. Okay, the pump is inefficient. So the blood isn't circulating as fast to get to oxygen and get it to the tissues and get back again to get the oxygen. All right, so histotoxic hypoxia. You were in my class last semester in the first unit, we talked about the mitochondria. And we talked about a poison that affected the mitochondria and affected the mitochondria's ability to use oxygen. Anybody remember what that poison was? Cyanide. Potassium cyanide affected one of the enzymes involved in electron transport. So this would be histotoxic. All right, the cells can't, this would be affecting cellular respiration. Not affecting pulmonary ventilation, not affecting external or internal respiration, but affecting cellular respiration. Now, of those three, which one would be affected by carbon monoxide? No. The hypemic. Notice ability of hemoglobin to bind oxygen. So if carbon monoxide is binding to oxygen, that's going to affect the ability of the hemoglobin to bind oxygen, right? So carbon monoxide falls under a hypemic hypoxia. So it's going to affect the ability because it's blocking the iron. Now, most of the time when we think of hypoxia, we think of hypoxic hypoxia. This is where we change the surrounding area around us. Okay? So maybe you're trapped in a room that doesn't have sufficient airflow and you're using up the oxygen in the room. Plus you're filling up the rest of the space with your own CO2. You're not getting a good ventilation. Okay? Or it may be because of altitude, where you are up at 12,000 feet elevation. And instead of having atmospheric CO2 of 160, it was 104, or whatever it was. So those are examples where your body tissues, your body functions are fine, but you're breathing in less oxygen than your body needs.
Like drowning, would that be considered?
Yeah.
I saw that diagnosis for it.
Yeah.
Okay.
Also, what about pneumonia? Pneumonia, you have normal oxygen, but it's not available to the blood because we've increased the diffusion distance. All right? So that's not, pneumonia's not changing the heart circulation rate or the hemoglobin available, but it's a barrier between the oxygen in the alveoli and the blood. So that's going to be an example of hypoxic hypoxia as well. We've changed the amount of oxygen available to the tissues, although it's normal in the alveoli, in the air, it's not, there's a barrier to it. Okay, so that would be hypoxia. Now I can't see it on my screen. Sorry, folks. All right, so these different slides just show some of the different factors, okay? So, you can read those on your own. What's going on here? Oh, I hit escape. So this is what I just mentioned, is the factors that I and then hypoxic. So any of these diseases, all right, as well as high altitude, any of these diseases that affect the ability of oxygen to move across the respiratory membrane are going to affect oxygen levels in the blood. So one of the causes of hypoxic hypoxia is high altitude, all right? So when we look at these numbers, you see something wrong here? 100% oxygen, 84% oxygen, 61% oxygen. What did I tell you?
It's always 21.
It's always 21. So what that is saying is it's 65% of the normal oxygen available. So it would be 65% of 21%. It would be 55% of 21%, okay? So it's not saying 55% of it's oxygen, but it's 55% of the 160 millimeters that we would have here. All right. So Nepal, Mount Everest is a third. So if our normal oxygen in our lungs at sea level is 104 millimeters of mercury, it would be about 34 up at Mount Everest. And yet people, a few, not a lot, have climbed to the top of Mount Everest without supplemental oxygen. I have no idea how they can imagine what their lung system. They're not thinking very clearly though, okay? Mount Denali in Alaska. Oh, no, here's Denver. So 84% is right about the level. So remember I said you can get 100% saturation at 90 or above. A lot of people that move to Denver, I always think I'm really, really lazy because I go to bed and I nap for like 3 or 4 hours a day the first month I'm there, and I keep forgetting. I know one time I was, my husband was he was at a meeting, like it was fly fishing and one of those things, you know, boondoggle where you go away to a conference and you end up having very few meetings, but just a lot of playtime. So he had taken the car and was up in the mountains, and I took the train from the airport and decided I wanted a milkshake at 5280. It's an ice cream store there in Denver, 2 blocks from where my husband's apartment used to be. So I thought, well, I can get a milkshake if I walk it off. And our house is about 4 miles from downtown. And so I decided I would walk to a particular restaurant and then I would hail Uber and go the rest of the way. Well, I got to that restaurant a lot faster than I thought I normally would. So I just kept walking. And I had those big suitcases, and it was on wheels. But because of the ice and weather in Denver, there's a lot of cracks in the sidewalk. That was the pain, was I'd have to keep changing the direction I was doing it to go over the cracks. And I was trying to impress my husband with how much I was walking, that I was actually walking home and pulling my big suitcase. And so I stopped and took pictures along the way to show him where I was. And then I started taking my heart rate. I was just walking, all right? So I'm about a quarter mile from home, half a mile from home. I'm walking, and sent it to him, HR 168, got to the house, went inside, took a shower, went to bed, and he comes home, I said, I looked at my phone, and he never responded. And I said, weren't you concerned? He goes, what do you mean? I said, I told you my heart rate was 168, and you didn't even blink, you never even called to see how I was doing. He said, I didn't know what you were talking about, I thought you said home runs, 168 home runs. Why would I be talking about that after baseball? But it was higher altitude, okay? So, one of the responses to prepare, remember what organ produces erythropoietin? Kidney, which we're also talking about in this unit, all right? So, obviously in one day, I'm not gonna get increased numbers of red blood cells. But one of the processes of acclimation to living in these higher altitudes is the production of more red blood cells. What did we look at here? So if you're at a higher altitude and your PO2 is lower, are you going to saturate every red blood cell? No. So to get the same amount of oxygen, if you're only saturating 50% of your red blood cells, to exaggerate, then your body needs to make twice as many red blood cells. Okay? That's one of the forms of acclimation, along with changes in blood flow and so on, and distribution within the body. What's that going to do to your viscosity? It's going to go up, all right? Unless you also increase blood volume by retaining more fluid, and that, whether it goes up or not, that increases peripheral resistance. The heart either has more volume to pump or it has to pump against a greater peripheral resistance. So those are changes. So when people go to climb Mount Whitney or Pikes Peak, or not even that so much Pikes Peak, but those higher mountains, they will often take drugs that will help to prevent the onset of high altitude sickness or mountain sickness. Anybody ever gotten mountain sickness? That has nothing to do with your physical fitness, by the way.
I did.
What, do you remember what altitude you were at?
I was in Arizona in the White Mountains. I don't remember.
Okay.
I was a kid.
You could have two perfectly fit people, and one gets it and one doesn't. First time, I don't want to talk, well, I've gotten it twice. Nausea and diarrhea are basically the way it shows up. I was hiking with my husband when we were dating, and I hadn't backpacked a lot. And we were backpacking the wilderness area here in Sierra, pitched our tents, and then the pass was about another 200 feet in elevation. So we went up there, and I wasn't physically exhausted, I wasn't even nauseated, but I could tell my heart rate was up. So I said, let's check our heart rates. This is before we had cell phones and all that, so he just checked his watch. And he was like 140. I said, I'm 210. And he was like, what? So I said, I feel fine. He goes, we're going back down. So we went back to our tent, and that was when the nausea and the diarrhea and stuff goes, okay, we're moving. So we put my backpack on a pole that we had between the two of us, and just a slight 2 or 3 foot climb over a boulder would make me nauseated. So the acclimation doesn't come in getting fit. It comes in allowing your body to adjust to the higher altitude by making more red blood cells and changing your redistribution. Taking acetaminophen the night before or for several nights. So I had a student, she and her boyfriend were getting ready to climb Alaska in the summer, and so they had gone to do Mount Whitney. And she had done everything the ranger said about taking the Tylenol and stuff, and I don't know how much she'd have to take, if it's 1 or 2. Her boyfriend hadn't. He started seeing log cabins with smoke coming out of them, like in the middle of the air over the valley as you looked out over the terrain and stuff. And she was really surprised because she thought he was more physically fit than she was, but it's how your body adjusts to this change. And people have died in their sleep. There was a schoolmate of my son's. She had gone off to Michigan to go to university, came back at Christmas break with her dad, and they had gone to climb Mount Whitney as a family tradition. And she was the one that passed away, not the dad. He woke up in the morning. They were on the trail and spent the night. When he woke up in the morning, she had passed and had died during her sleep. So some people have underlying pulmonary hypertension conditions that can be affected. So there's a variety of events. So there's a range. I want you to know a couple of terms. And one is HAPE and the other is HACE. H-A-C-E and H-A-P-E. pulmonary edema and high altitude cerebral edema. The causes are not well known. But both of these are caused by shifts in water volume as the body tries to adjust and change the circulatory function. The high altitude cerebral edema is what HMS is another name for high altitude sickness, is what leads to these mental and difficulty thinking. Unfortunately, it also makes the people, when they start, this is caused by hate, when they start to have this, they aren't thinking well enough. It's almost like a reverse of narcosis and diving, and you don't mentally understand the danger that you're in. So someone else has to make the decision for you to return to a lower altitude. All right, so these are just, you don't have to be able to discuss these or describe these just because, again, it's not perfectly well understood, but it's just thought that this is how the body tries to compensate for it, and it isn't given enough time, then it can lead to the symptoms of pulmonary and cerebral edema. Okay. So when we talk on Thursday, we're going to talk about control of respiration and what the body tries to do and why it changes breathing patterns. But as you are in higher altitude, are you going to be taking deeper, more frequent breaths or shallower, more frequent breaths? Thinking about our alveolar ventilation and pulmonary ventilation that we talked about last week. Deeper, okay? So if you're taking a deep breath, I'm getting in more oxygen, right? But I'm also blowing off CO2. And that can lead, we'll see on next week, that'll affect, when we get to urinary system, that affects our pH balance. Because if we blow off too much CO2, then you're not getting enough acidity, enough hydrogen ions, and you can go into alkalosis. All right, so you think that'd be fine, to get in the oxygen, but it's the CO2 that you're getting rid of. If you get rid of too much, that can be the problem. Okay, so we're going to stop here. I want to get the lab in with our BioPack, and we will do the carbon dioxide on Thursday, because we're going to talk about the role of carbon dioxide that it plays with control and regulation as well. Okay, so why don't you guys, do you want some study time? Okay, check with me about 8:30. And we'll see, go from there. Okay, while you're doing that, I'm going to pull the BioPacks up and get that started. There are 4, yeah, because the 5th one is not till the end. Well, let me see. Actually, I can answer the 5th one because it has to do with what we've already talked about. So this has to do with our pulmonary perfusion. So this is the pulmonary ventilation perfusion that we were talking about earlier. Yep, they're the same, it's just a diagram.
I just have to.
Olfactory, so see how these have multiple nuclei? But then there's a region of the cell where there are nuclei. And olfactory, you're going to have nuclei all the way up because they have the 2 different, right? The bipolar cells, yeah. So you can't go by this.